Okay, hello everyone. Welcome to Lection 7. Yeah, this is the one I've been looking forward to because this is actually what I work on in my day-to-day work. So today we're going to talk about neutrino astronomy and how you can use neutrinos to figure out stuff, or at least try to figure out stuff that's going on in space. But maybe first we should talk about what actually a neutrino is. And so the idea of the neutrino came up in the context of nuclear decays. So about 100 years ago, people figured out that some usually pretty heavy nuclei will kind of spit out particles when they decay from one type of particle to another. And the first of these decays that was discovered is something called an alpha decay. So for example, certain uranium isotopes will sometimes spit out a helium nucleus, and then, in this case, for example, turn into thorium. And when you measure what energy these alpha particles have, so this is for different, mostly plutonium and americium isotopes. If you measure the energy of these alpha particles, you get pretty much the same energy all the time. Within uncertainties, this is not a perfect line. That's just because whenever you measure something, there's always some little error you're going to make. Some of these you're going to see there's like a second peak, but that's just because sometimes you can end up in a reaction where this nucleus that results in is in what's called an excited state, where the nucleus actually has more energy than the ground state. And then it just gives a little less energy to the alpha particle, and usually it will then eventually spit out a gamma ray and then get into this lower energy state. And if you think about this in terms of physics, it makes a lot of sense that you would always get pretty much the same numbers here, because it's kind of like this Newton's cradle toy. If you push some of these balls back and let them slam against it, you will always see the same number of balls kind of move on the other side. And that's because in these interactions you have to conserve energy and you have to conserve momentum. And if you do the math, it turns out that there is only one solution that you can conserve both. And so because of that, you can always have only one specific energy for these alpha particles in these decays. But then there's also beta decay, in which the nucleus spits out an electron. And for this, if you plot how many of these electrons you see with what energy, you can see that you basically see all different kind of energies, which is weird because this obviously, the nucleus you get afterwards always has the same energy. So in principle, the energy that gets released should be the same every time, but it very clearly isn't. So that stumped people quite a bit. And the first thing you think about is, well, maybe energy is just not conserved always. Maybe we were kind of wrong about this for hundreds of years. But the weird thing is, there's very clearly a maximum energy here. And this maximum energy is the energy, you can measure the mass of the nucleus before this decay, and you can measure it afterwards. And this maximum energy is pretty much exactly the difference between the two masses. So it very clearly, at least in some context, conserves energy. So the solution to this, well, he didn't really think of it as a solution at the time, but Wolfgang Pauli came up with the idea, well, maybe there's a third particle there that we just don't see. And he wrote this letter, which I'm just showing because it's addressed to the dear radioactive ladies and gentlemen, which I just find lovely. But he said, well, maybe there's an extra particle and we just don't see it. And this made people feel kind of uneasy about it because, you're just proposing something there that you cannot see. And at the time, it was pretty, nobody could really think of a good way you could actually prove this. So it was kind of a little uneasy. And Pauli called this particle the neutron, which was a problem because there's another particle you probably heard of that's also called the neutron that was discovered at roughly the same time. And so that was kind of a bit annoying that there's now two particles with the same name. So some physicists in Rome started jokingly calling it the neutrino because ino in Italian is like for little things. So it was like the little neutral particle. And then eventually Enrico Fermi, who was one of those Italian physicists, mentioned it at a conference, and then the name stuck, so that's why we call it neutrino now. So it's basically means like the little neutral particle. And this was eventually shown with nuclear reactors. This was in the 50s. You could build nuclear power plants that produce a ton of neutrinos, and they eventually managed to detect it and prove that neutrinos exist. But that's particle physics. We want to talk about astrophysics today. So let's talk about the other big nuclear reactor we have, and that's our sun. Quite a while ago by now, I showed this main production cycle of how the sun produces energy. And it starts with two hydrogen cores, so two protons, reacting, and one of them turns into a neutron. And at the time, there was this little thingy here, that's a neutrino. So these get produced in these chains. And you can model this, and you can calculate how many of these neutrinos you should see. And then there's also other fusion reactions that I talked about that also will produce neutrinos. So there was the CNO cycle, for example. And this shows how many neutrinos of these different cycles will produce. You can see the most, at least for our sun, the most neutrinos are produced by this chain reaction. And one thing to really notice is this is a logarithmic scale again. So if you go from here to here, that's 10 times. And this is a huge number. This is 10 to the 11. So a 1 with 11 zeros behind it. So that's 100 billion. And this is in centimeter per second per mega electron volt, so per kind of energy interval. And so energy interval is, it's like roughly 1. So you can just kind of ignore this per MeV. So we're talking about 100 billion, roughly, of these neutrinos per square centimeter, so like this size, per second. So that's a ton of neutrinos. But they tend to not interact a lot. So, there's, I don't know how many billion neutrinos going through your body every second. I don't want to do the math right now, but it's a lot. On average, you're probably going to interact with one of them throughout your life. Some of you won't interact with any, some of you maybe with 2. Nobody knows, but they just really don't do a lot. And the question I'm always asked when I talk about this is, how do you measure a particle that never interacts with anything? And the answer is you don't most of the time. So whatever detector you're going to try to build, you're going to miss 99.99 and then a bunch more % of the neutrinos that are there. That's just unavoidable. So the way I like to think about it is it's kind of like opinion polling. Like if you want to know who's going to win the next election or something, you're not going to track down every voter and ask them, right? You're just going to pick maybe a couple thousand people, hope that it's the people you picked are kind of representative, and then from that you can draw conclusions about like the bigger picture. That's essentially what we're doing. And so for these solar neutrinos, if you want to see a lot of them, you still need a pretty big detector. And that's going to be a theme in this talk. You're just going to look for rarer and rarer neutrinos, and the detectors are just going to get bigger and bigger. And you can maybe try to think how big do you think it's going to get? Because it's going to get really big. So the first attempt to detect these solar neutrinos was something called the Homestake mine experiment that was in an abandoned mine shaft in, I think, North Dakota, one of the Dakotas. South? Okay, thanks. And they basically built this giant tank here. So here's a guy standing. This is a picture from later. And they filled it with what's essentially cleaning fluid. Because there's a certain reaction that can happen. So if you have argon, which is a noble gas, and you have a very specific isotope of this, what will happen is it will sometimes basically the nucleus of the atom will absorb one of the electrons in the outer shell. And then you get chlorine, and it will emit a neutrino. Now, you can tell that this is happening because this electron here was absorbed, there's now basically a free space in the shell structure of this atom. And the electron that gets absorbed is usually in one of the lower energy states. So what happens is one of the other electrons in the shell is going to rush into this gap that's now available. That releases energy, and that will kick another electron out of the shell. So they're called Auger electrons, named after Pierre Auger, the same guy that this observatory 2 weeks ago was named after. And from this, you can tell that this decay is happening. Now, the interesting thing about this reaction is that you can reverse it. If you have a bunch of chlorine, and that's why they use cleaning fluid, because that is some carbon chloride compound, and you basically shoot a bunch of neutrinos at it, occasionally this will turn into argon. And so now this is, you have a chlorine compound that's liquid, and then you have a tiny amount of argon in there. And this argon, as I said, will occasionally decay. So what they did is they filled this giant tank, then let it stay for a while, and then after a week or so, a handful of these chlorine atoms in the tank will have turned into argon. So, yes?
I saw like a different reaction to do this. It's like a thing where like some isotope was turned into like a different isotope with a neutrino, and that like emitted an X-ray burst specifically.
I'm not entirely sure. It might be for the reactor neutrinos. I don't know what exactly you're referring to. But it's very well possible that you're right, because this is kind of how most neutrino detections in the early days worked, where you had like some isotope turning into another isotope. So it makes a lot of sense to me that for some experiment they would use something else. It's a bit more complicated. So there is a reaction that's a little bit like that. That's unfortunately an experiment I had to skip for time reasons. It's called the Sudbury Neutrino Observatory that does something kind of like that. So there are reactions like that you can use for detection. That's true. Okay, where were we? Oh yeah, so we have some of this chlorine in our big tank being turned into argon. So then after a week, what you can do is you just pump a bunch of helium through it. And this helium is going to take the argon with it, because you have now little gas bubbles in there and the argon is in there. Then you just put this, you try to get as much of the argon out of the helium as you can, and you just see if you see these decays. And then if you see this decay here, you know that a certain number of for every decay, you know that this interaction has to have happened once. And then from that, you can calculate how many solar neutrinos there are, if you have an idea how likely this interaction is. And from theory, you can calculate this pretty easy by just observing this decay. Because these are basically the same reaction going different directions. And in theory, it's fairly easy in this situation to calculate what's called the cross-section, basically the likelihood that this interaction happens. So they did this, and they only observed about 2/3 of the neutrinos that they expected based on the nuclear reactions that are going on in the sun. At the time, this was in the 50s, so it was like late 50s, early 60s, and the sun was not understood that well, so you could, and the neutrino also was kind of a new particle, so you could kind of explain it with maybe we don't understand the sun well enough, maybe neutrinos act a bit differently than we thought they do, so this was weird, but it was not, oh no, what's going on, we have no idea, weird. But there was another problem that emerged very soon after that, and that's, so this thing with not seeing enough solar neutrinos is called the solar neutrino problem, and soon after that we got the atmospheric neutrino problem. Because I've shown this picture a couple times now. So this happens in air showers a lot. So you have your pion that gets produced by collisions in particles in these air showers. Then that decays into a muon, and then that muon decays into an electron. And you can see here, every time this so the first decay happens here, and the muon, has a different direction than the pion. And then here with the electron, the same happens again. And that's because you also have a neutrino emitted here, and that neutrino takes away some of the momentum, and that's why it looks like the muon, and here the electron gets a little kick. If you look closely, there's like a second time where the direction changes. I'm fairly sure that is just basically the electron colliding with one of the atoms that are in this in the substance that's used for the detection. So that's just a collision. Please ignore that. And the thing is, we can measure how many muons we see and how many electrons we see. So we know it pretty well how many neutrinos we should see from this. So there's really no wiggle room. And there was a detector that could detect these. That was called Kamiokande, which stands for the Kamioka nuclear decay experiment. And it was later upgraded to Super Kamiokande. And for some reason, I couldn't find any pictures of the original Kamiokande. They don't put these online. I don't know why. And the reason it was built was actually didn't have anything to do with neutrinos. It was, at the time, there was a popular theory that theorists came up with to basically describe all the forces we see by just one fundamental interaction. And if this theory was true, it predicted that occasionally, but extremely rarely, protons should sometimes decay. And if this decay happens, it would it would produce Cherenkov light. So what you do is you build a giant, basically pool of water, because water has hydrogen in it, which is basically just a proton. And then you put a lot of these photomultipliers here. So these are these light detectors that can see tiny flashes of light. And so this is two physicists on a boat. Eventually this gets filled up all the way. And you also want to do this deep underground. So this is about 1,000 meters, so 3,000 something feet below the ground in an old mine. And that's just to shield it from any, for example, cosmic rays that might come from above. And it turns out protons don't decay, so they didn't see that. So they had enough time on their hands to just look at other stuff. And it turns out you can see neutrinos. So neutrinos that interact in this water will produce a Cherenkov light that I mentioned last week. So you have either a muon or an electron being produced, and then moving through the water faster than light moves in there. And you get these shock waves. And if it's a muon, then you basically just have a muon, but muons can travel a fairly long distance. So that's why you get this ring that's a little wider compared to the electron here. But it's also very smooth because it's basically just a single particle. An electron, on the other hand, will produce a shower. So it will just bump into other electrons in the water, for example, and then produce new electrons and so on, and you get these showers. So first of all, the shower is shorter, so that's why this ring is thinner. And now we're talking about multiple particles, so that's why you see this kind of like fuzzy edge here. So now we can measure. Okay, so if we see a muon or an electron suddenly pop up in the middle of our water tank, then that must have been from a neutrino because nothing else should be able to reach it. And from that we can then calculate how many neutrinos do we have interacting in a tank. And electrons, they saw pretty much what they expected. For muons, again, they saw too few. And this was really weird because, again, we know exactly how many muons we get out of air showers, so we know exactly how many of these muon neutrinos should be produced. And for the explanation, unfortunately, we have to get a little bit into particle physics. So this is a big part of our standard model. I'm leaving out some particles that are responsible for interactions. And in the standard model, so basically you are down here. So you have your up quark and your down quark, and neutrons and protons are made of these quarks. And then from that you can build your nucleus, and then you have electrons running around the nucleus, and that's basically the particles you will interact usually in your day-to-day life. And then you have your electron neutrino, but then there's a whole second and third kind of generation of particles that are pretty much the same as like these four, except they have different masses. I don't know, there's no good explanation like why they're here or what they're doing. It's just they are there. We can measure them. And the important thing is that if you go from the left here to the right, all these particles tend to get heavier and heavier. And now the way neutrinos interact is you have your electron, your muon, and your tau. So you have electron, and then its two kind of heavier siblings. And you also have neutrinos that then are electron neutrinos, muon neutrinos, and tau neutrinos. And a neutrino will only interact with something called the weak interaction, which, as the name suggests, is weak, which is why they don't like to interact. And there's two ways you can do this. There's something called the neutral current interaction, where basically the neutrino will just kind of bump into something. So you have your neutrino, then it emits a particle called a Z boson, and then it just kind of goes on its way, and this particle will then, for example, bump into a down quark in one nucleus and just give it a little bump. This is pretty hard to see at lower energies because, you just have a little bump, like it's not actually doing much. But the other interaction it can do is called the charge current interaction, and what will happen then is an electron neutrino will turn into an electron, and will also turn, for example, a down quark into an up quark. And this is the interaction that we saw with the Homestake-Meyer experiment for the solar neutrinos. Now, the interesting thing for that experiment is a muon neutrino will not be able to do this because a neutrino with the energy of solar neutrinos does not have enough energy to produce a muon because that's heavier. So this interaction for the Homestake-Meyer experiment only works for electron neutrinos. Because if an electron neutrino interacts, it will give you an electron, a muon neutrino will give you a muon, tau neutrino will give you a tau, and so on. And the thing is that because neutrinos are so small, everyone just kind of assumed they didn't have masses. Because, like, why would they? We don't see anything that suggests they have it. But if you say that these neutrinos have masses, and the different neutrino kinds of neutrinos have different masses that are just very slightly different, then you have something called neutrino oscillations, which sounds weird, but it's actually something that basically, like, once you accept that neutrinos have mass, then it's just something that falls right out of the theory. It's not actually as weird as it sounds at first. But what will happen then is that, for example, if you have start with an electron neutrino, it can just kind of turn into a muon neutrino or a tau neutrino. So this here shows, if you start with an electron neutrino here, this shows you the probability that after it propagates a certain time, and this is basically depends on the ratio between the distance that the neutrino traveled and the energy it has. And this shows that after a while, most of the electron neutrinos will have turned into, for example, muon neutrinos and tau neutrinos. So those are the blue and green line. So if neutrinos have mass, then a way we could explain the Homestake-Meyer experiment and also the atmospheric neutrino problem is that, well, these electron neutrinos just have, some of them have turned into muon neutrinos and tau neutrinos, and then we cannot see them anymore. And the same could have happened to the muon neutrinos from the air showers. But, is there a way to test it? And it turns out there is, because you can see this happens on the depends on the energy and the distance. And with Kamiokande, just from kind of the direction that this Cherenkov ring we're seeing is pointing, we can tell where the neutrino came from. And if they're from air showers, well, if we look straight up, then it's going to be from an air shower that happened like right above us. But if we just look down, then that's from an air shower that happened at the other side of the Earth. So, that's a lot further away. So depending on which direction we're looking, we see air showers from different parts of the world. So the neutrinos that we see from these air showers will have traveled different distances. And also from the light, from the amount of light that these particles produce, we can also detect the energy. And that's what they did with Kamiokande. So this is basically, so each column here is just a different energy that they looked at. And then the top row is how many electron neutrinos they saw, and then the bottom row is how many muon neutrinos they saw. And then this axis here is the direction, and these brighter lines show you what you would expect if there were no neutrino oscillations. And then the thinner dark lines show you what you would expect if there are neutrino oscillations. And then these little crosses here is what they actually measured. And you can see consistently, you see the number of neutrinos you see from different directions matches very well with what you expect for neutrino oscillations. And this is, experiments like these are done these days quite a lot to just test different aspects of neutrino oscillations. You may have heard of DUNE, which is then currently, not the movie, the detector they're building at Fermilab. That's essentially trying to do the same thing, except you don't use naturally occurring neutrinos. They build an accelerator at Fermilab and just shoot and produce neutrinos that way. But this is a very popular, or well, very interesting thing to do these days in neutrino physics. And also Super Kamiokande is currently being upgraded to Hyper Kamiokande, which is also supposed to probe these neutrino oscillations. Because as far as we can tell, they look very kind of what you would expect for the standard model. But there are some interactions in there that we could expect under certain theories, so this is a really big topic right now in particle physics. Yes?
In this oscillation, they all have masses, they're very small masses. And I know you only know ratios of masses, you don't know any absolute mass.
Yes.
But the difference in mass will, how does it energy interchange? I mean, is there a way you can anyway an explanation as to where this mass change comes from?
I had, so there is a fairly elegant way to explain it. It just takes like an hour. Okay. So essentially, what's happening is, we say we see an electron neutrino if there's the interaction produces an electron. We say we see a mu neutrino if the interaction produces a mu neutrino. But there's also a way you can think of those in these what's called mass states. So you have a neutrino with mass 1, you have a neutrino with mass 2. And it kind of depends on what you see as like the natural thing to look at. Because in theory, it's equivalent. You can think of it both ways. We choose to think of them in these states because that's what we can actually measure. But the thing is that, for example, an electron neutrino will consist of a combination of these three mass states. If you think of it in quantum mechanics, kind of like a superposition of different, for example, locations, it's kind of like this.
So you're not looking at a pure state in any case?
Yes. You basically have a mixing of the different mass states in there. And that's basically why you get these oscillations, because they will kind of change at different rates. And then you can end up with kind of the combination of states that corresponds to the mu neutrino, for example. That's the kind of quick attempt to explain it. Okay, so now we mostly understand how neutrinos work. Can we actually see stuff with them? And unfortunately, we don't actually see a lot with neutrinos because, again, they're kind of hard to measure. But the first big thing, other than a sun, that we could see with neutrinos was a supernova, and it was a very particular one called the supernova 1987A. That was obviously happened in 1987. It was the first one that happened that year, or that they saw that year, so that's why it's A. That's how this naming convention works. And it happened in this thing called the Large Magellanic Cloud, which is a fairly close by dwarf galaxy. And in this picture, this is the supernova. It tends to be, these things are incredibly bright, so it's fairly easy to see here. And since last week someone asked about it, we actually can see the remnant of this. So it has the shape of a ring, so this is probably the neutron star that was left afterwards. And then these are the ejecta, and you can kind of see them moving, and eventually they bump against this ring, and you get these bright emissions. But at the time, people were really excited because Kamiokande was running. And so someone from Penn State wrote them and was like, hey, this is really exciting. We saw a supernova. Just, hey, do you see this? And turns out they saw it. This is the actual printout that someone, I guess, scanned in of how many neutrino interactions they saw at Kamiokande. And you can see, so these little dots here give you the rate, and you see this giant spike here. Time on this, by the way, goes from right to left for some reason. You can also tell they got really lucky because this is when the detector was down for maintenance, so they turned it on just in time. And they saw about 11 neutrinos, which is enough to tell you that there definitely is something. But again, neutrinos very rarely interact. But it was just from seeing it at the same time as the supernova happened, could tell you that, this must be where they came from. And interestingly, these neutrinos actually came slightly earlier than the light from the supernova, which sounds weird. But the thing is that these interactions that produce both the light from the supernova and the neutrinos happen at the very core of the star that's collapsing. So as the star is collapsing, it's getting incredibly dense, and so the light has a hard time to get out of there. But neutrinos, because they hardly ever interact with anything, they can just go out there. So it takes the light a little bit to get out of the center. Neutrinos just go out. That's why you see them slightly earlier. Yes?
Do all three neutrinos travel at about the same speed?
Yeah, roughly. They have like very slightly different masses, but these differences are so tiny that it essentially doesn't matter. And this is actually because if we know the energy of these neutrinos, and from that we can, if we know if we know how much slower than light they travel, you can measure the mass. But because we couldn't see any difference in the travel speed from that to the accuracy that we can measure, and because they travel quite a very long distance, so even if there was just a tiny percentage, like less than 0.000 something percent difference in the travel time, we would have seen it. And from this, you can actually kind of put a constraint on how heavy these neutrinos can be. And for a really long time, this was kind of the most stringent upper bound on the mass that these neutrinos can have. Yeah?
Mass you move less than the speed of light. Does the nutritional concentration, if there is such, increase when we have solar flare?
I don't know, but I'm pretty sure it wouldn't be measurable. I don't think it would do too much, because that's, the neutrinos are produced at the core of the sun, and these flares happen on the outside. And it's definitely not something we could measure, even if there is a small effect. But speaking of small effects we can measure, there's so this is the only supernova, unfortunately, that happened, or you can argue, fortunately, that happened so close to us. So this is the only time we actually got neutrinos from a supernova. But there is kind of an interesting thing that probably tells you more about physicists than about physics. And there's a star called Betelgeuse that is in our galaxy, so it's really close. It's fortunately still far away enough that when it explodes, it's not going to do too much to us. But over the last couple of years, it's been changing in brightness and even in shape. So these are two different pictures, and you can see that even the shape of the star has changed. And it's a red giant, so we think it's pretty close to going supernova. But this could happen tomorrow, it could happen in several thousand years. There's really no way to tell. But if you're doing neutrino physics, there's always, sometimes you hear rumors that some detector is detecting more neutrinos than usual, and there might be something happening, but so far nothing had happened. But if we get lucky, we might actually be able to see a second supernova with neutrinos fairly soon-ish, hopefully. So that's neutrinos from stars. Can we go back to our problem with cosmic rays? We still don't know too well where they're coming from. And we would like to basically use neutrinos to figure out where cosmic rays come from. And the idea is basically the same as with the other ones, with gamma rays. You have your cosmic rays being accelerated somewhere, and they will bump into something, and that will produce neutrinos. The problem is, so this here on the left shows you how many neutrinos from different sources we expect. And so this is, from the sun, from supernovae, nuclear reactors. This is what we expect from these air showers in our atmosphere. And then what we actually expect from the cosmic rays from space is down here. So it's tiny amounts of neutrinos. So we need to build even bigger detectors, and they need to be so big that we just have to take some matter to as a target that's just there naturally. There's a question?
What does cosmogenic mean? Like,
Oh.
the peak one is the ear shells, right?
These ones, I get to them in a bit. Those are actually the ones I'm looking for, so good question. So, but you know, we get there. Let's try to find those neutrinos from the cosmic ray sources first. So for this, we need some detection material that's ideally transparent and that's fairly dense and that's naturally occurring in large amounts, and that we can see the strength of light from if neutrinos interact. And kind of the best and almost only material that we have for this is water. So there's experiments that try to set this up in basically build Kamiokande in the lakes or in the ocean. And the big one is that's currently under construction is called KM3net, which just means like the cubic kilometer neutrino detector. And they have these little spheres here that are have little photomultipliers in here, so that are supposed to see the strength of light if neutrinos interact in there. And the way they work is they have these kind of spheres that have a bunch of these detectors kind of curled up with cables in them, and they get dropped on the ocean floor. There they uncurl, they have little balloons on top, and then they just kind of drift in the water. So that's currently under construction in the Mediterranean. But it turns out building stuff underwater is really hard. So they're currently working on this. There's another experiment that's been working for a while now that's called Baikal, because it's in Lake Baikal, which is an incredibly deep lake. It's like 1,000 meters deep. And the nice thing about this lake is that in the winter, it's in Siberia, so in the winter it freezes. So instead of trying to do everything from boat, you can just walk on there, dig a hole or drill a hole into the ice, and then you can deploy again these photomultipliers on basically cables that then just float in the water. So these are pretty much under construction right now. They haven't really seen too much interesting stuff by now, but they're working on it. But the big one that's actually seen stuff is called IceCube. That's basically right next to the South Pole. And what they did for that is they drilled holes almost all the way through the ice sheet, which is almost 3 kilometers thick, so 2 miles almost all the way to the bedrock. And then they put these things in here. This is called a digital optical module. It has a little photomultiplier here, again, to measure this Cherenkov light. Then signal gets digitized and then sent up on a cable to be analyzed. And building this was a giant thing, but it was still decided that this was still easier than building anything in the sea. So they had to, first of all, dig a bunch of trenches to bury the cables in so that no one trips on them. Because it's the South Pole, everything they used at the time had to be flown in by airplanes, including just fuel. These days, there are some land routes that they sometimes use. They have like a little caravan. The holes they drilled with what's called a hot water drill, so it's fairly easy. You just push hot water into the hole, you melt the ice, get the water out again. And it's this giant thing. It takes like 10 people to operate. It's basically looks like a little city. And then eventually you have the holes, and you can see here there's a little one of these digital optical modules called DOMS is being lowered into. And what you want to do with that then is if a neutrino interacts, hang on, you get something like this. So this is some of these neutrinos you're seeing. So you have in this case, it's a muon neutrino, so you have a muon being produced here. You see a big blob here, so that's because as this muon is produced, you still give a kick to one of the nuclei in the ice, and that also produces a shower there. And then, in this case, you only see the shower, and you have light being emitted there, and each little blob you see here is one of these digital optical modules. And the size of the blob tells you how much light it saw, and the color tells you kind of at what time it arrived. A big problem with ice cube that's kind of annoying is that there's little air bubbles in the ice, and that scatters the light. So the light that's emitted doesn't go directly to the detector. It's going to kind of bounce around in the ice a little bit. So that makes it kind of hard to figure out where exactly the signal came from. So if you have a shower, you basically, even though the chunk of light itself is emitted on a cone, but because it's scattered so much, you just get these little kind of blobs. But if you get a muon, which you can kind of see here, as it's moving through here, that you can still kind of figure out the trajectory of the muon. And yeah, this is, so by the way, the first neutrinos were all named after Sesame Street characters. So you have, the first two were called Ernie and Bert. Yeah?
What kind of neutrino was that last one?
Big Bird, I think it was a
muon. Like a huge,
oh,
blob.
Dr. Station.
Like,
Yeah.
is that like one detector that causes most of the neutrinos?
Yes, hang on. Let me pause this so we get a good look.
Is that like a
So,
detector that's in the directly or something?
yeah, well, so this is, so the colors tell you the time. So if it's red, that means it was very early. So you can tell that the detector that, or the sensors that measured this has to be really close to where the original interaction was. So you have in the initial interaction between the neutrino and the ice, you get a particle shower that produces a lot of light. And if it just happens to occur really close to one of your detectors, then you see a lot of light. So that's what this is.
That's just like one or two detectors.
This red blob is just one detector, but it's because it's right next to the shower, it sees so much light that it, look there. Yes. And I mean, Big Bird also happens to be probably one of the highest energy neutrinos ever observed. There's actually, are there any soccer fans here? Anyone know Jürgen Klopp, German soccer coach? There's one that's the last one you're going to see. It's called Kloppo unofficially. You're never going to hear anyone like in a paper or something write it. It's named after a soccer trainer, semi-officially. I think this one is it. This might actually be the highest energy neutrino that was ever observed so far. But it's hard to tell because it kind of came from the outside, so you don't really know how much light it emitted here. So if you have a muon neutrino now, you can see that as it moves here, you can, from just when the light arrives at different detectors, because it's traveling such a long time, you can figure out fairly precisely where it's coming from. You can, within about half a degree, which is for astronomy actually pretty bad, but it's good enough. And so what you can do then, you just take all your neutrinos and you see, okay, what direction are they coming from? And that's what this map is. So basically, if it's white, then there's kind of an average number of neutrinos. If it's bluish, there's like slightly more neutrinos coming from there than you would expect, but it's not enough to really, it might just be a coincidence. But there's this little spot here that actually has so much more neutrinos that you cannot coming from there that you cannot explain it by just being a coincidence. And what you can do then is you can look, okay, is there anything interesting? And turns out there is. It's a thing called NGC 1068, also known as Messier 77. So this guy Messier that we talked about some weeks ago also found it. And it looks like this. It's a galaxy, and at first look, it looks fairly normal. It's just a galaxy. But the interesting thing is that the core of this galaxy is a lot brighter than you would expect. And if you look more closely, so this is with X-rays. So with X-rays, you tend to be able to see very hot stuff. And you can see there's a lot of high energy X-rays coming from here. So whatever's going on here has to be, has to produce a lot of heat. And then if you use radio, where you can kind of see through some of this dust you have here, so that's this bluish color, you can see a jet here. So here's a black hole, and then you can see a jet coming from here, roughly where you see all these X-rays from. So what this seems to be, it is one of these active galactic nuclei where you have a jet shooting out of a supermassive black hole, but there's just stuff in the way that kind of stops the jet. But that makes it a really good candidate for being a neutrino source or cosmic ray source, because that will produce these shock waves that we talked about last week that will produce these high energy cosmic rays. So this makes NGC 1068 a really likely source for cosmic rays, and the fact that we see actually neutrinos coming from there tells us that we're probably right, that this is the kind of source that will produce cosmic rays. Now, the problem is that because the ice cube cannot reconstruct the direction of the neutrinos too well, if you look a certain direction, there might just coincidentally be a lot of stuff there that may or may not be where the neutrino came from. But what we can also use is the information about when the neutrino came. So what's IceCube now doing now also is it's sending out what's called real-time alerts. So it's basically an email list that you can sign up to, and every time IceCube sees a neutrino from a direction, IceCube sees a neutrino that it thinks is really interesting, it will send out an alert to basically whoever is interested, say, hey, look, in this direction in the sky, there might be something going on there. And one of the times they did this, they basically had a bunch of telescopes look in that direction, and they had MAGIC and Fermi, so these are these gamma ray telescopes that we talked about last week. They looked in the direction, so this red and this gray line is where IceCube thinks the neutrino came from. And then with gamma rays, you can also see more gamma rays than usual coming from somewhere inside this circle. And because with gamma rays you have a much better resolution about where they came from, you can actually pinpoint this to an object called TXS 0506056. The name is just because it was discovered by a telescope in Texas, and then this has to do with the position where it is. So very creatively named. Unfortunately, it's so far away that there's really no good pictures. So this is kind of an artist's picture. So what it seems to be is, again, one of these supermassive black holes that accretes matter and then shoots out a jet. So it's one of these blazars with very long baseline interferometry. With radio telescopes, you can actually see this jet. So that is what that jet looks like over different years. And you can see, so this is where the black hole is, and then you see this matter shooting out here. And over the years, you can actually see it change its shape, and it has a little bend. So we can actually see the jet. We know that there is a jet shooting out. But what made the case that this is actually a neutrino source very convincing was that after they saw this neutrino coming from that direction, IceCube, as I said, sent out an alert, and so a bunch of telescopes looked there. And this is kind of showing you what they saw. So each row here is a different type of telescope. And then this is basically just a timeline of how much they saw from there. And here it's just kind of, the second half here is just kind of a zoomed in time. You can see especially gamma rays, they didn't have a lot of observations, but sometime before they looked at it, and there was not that much coming from there. And then after this neutrino alert, they looked at it again, and it produced a lot of gamma rays. Same here, this is with lower energy gamma rays, you again see this increase in gamma rays just before the neutrino, or at the time of the neutrino, and same also with radio. So just at the time when we saw a neutrino come from there, we also saw this source kind of flaring up. It's called blazar flare. And because you can calculate what is the likelihood that just by pure coincidence we have one of these flaring blazars just at the time and in the direction where we see neutrino coming from, you can tell that just by chance it's very unlikely that this just happened. So from these observations we can tell that probably these kinds of sources are responsible for cosmic rays. But there's still a bit unsatisfying, because if we look at kind of the energies of the cosmic rays we see, and we compare this to gamma rays and the neutrinos IceCube sees. So the gamma rays are here, IceCube is here. You can see we're still a lot short of the energies of the highest energies of cosmic rays we're seeing. So we can tell that there are definitely particles being accelerated to really high energies, but to really kind of nail this down that it's actually the very, very highest energies coming, cosmic rays coming from there, we would like to be able to see neutrinos all the way here. And there's a second thing that we would like to find out, and that is if you kind of look at the very, very highest energy cosmic rays, there is a drop-off in the flux here. And there has been a theory that, or a fairly solid prediction, that if a cosmic ray has enough energy, it should be able to interact with this cosmic ray background. So this is like the very first light in the universe. It's still there, and it's because this happened in the entire universe, it's the most common form of light we have. It's just very low energy. And so if a cosmic ray has enough energy, it will interact with photons from the cosmic microwave background. And this interaction will do two things. It will, first of all, the cosmic ray is going to lose energy, and that could explain why we have this cutoff here. And the other thing is it's going to produce neutrinos, and that are these cosmogenic neutrinos that you asked about. So we would like to be able to see, if we can see neutrinos at these energies, then we could confirm that this is actually what's happening and that this is why there's this drop-off. Now, the problem is, again, we need an even bigger detector because these neutrinos are just getting rarer and rarer. Is that a question? No? Okay. So we need an even bigger detector, and if IceCube was already really expensive, you cannot just build a bunch of ice cubes and just get a bigger detector that way. So instead we use radio waves, and we use something called the Ascarian effect, discovered by this guy, Gorgon Ascarian. And the idea is that if you have a particle shower, just kind of like Cherenkov light, it will emit radio waves in this cone. But with radio signals, there is an interesting effect, and that is because you don't have a single particle in your shower. You have a bunch of particles. They all emit their own light, and this light is going to overlap. But if you have a very short wavelength, so what's happening here is this gray line is just kind of a wave that I'm just shifting back and forth randomly. And then this blue line is just I'm adding this wave to this blue line. And if it's a short wavelength, sometimes the maxima will overlap. Sometimes they're going to be off by each other, and the signal will actually get weaker. But if you have a very long wavelength, then these shifts are all gonna line up more or less perfectly, and you will always get a stronger signal. And at radio wavelength, the wavelength of the signal is actually bigger than the shower. So all the individual particles in the shower will produce a signal that just lines up perfectly. And so as the number of particles in the shower increases, which happens if you have higher and higher energies, the signal will get stronger and stronger. So at really high energies, the radio signal is actually much brighter than the optical signal. And the nice thing about radio signals is they can actually travel through stuff, right? You probably have cell phone reception here, but you cannot see outside, right? And so if we just put a bunch of radio antennas in the ice, we can detect these radio signals from a really long distance. So that's the project I'm currently working on. It's built here in Greenland at a place called Summit Station, because there's also a lot of ice. Basically, that's why we're there. And we're currently trying to build an array of these radio stations. And this is what they look like on the surface, because most of the stuff is underground. But basically what we do is we drill a bunch of holes, then we put radio antennas down here. And if a neutrino interacts here, it will produce these radio signals, again, at this Cherenkov ring. And then the radio signals can travel a mile or more through the ice. And we're going to hopefully be able to detect them, and then we know that there was a neutrino. Unfortunately, I'm kind of running out of time, so I should go quickly through this. So we're building this right now. We have this drill here that's developed by the British Antarctic Survey, and kind of have a tent around it. So you drill these holes to about 100 meters deep. And then once you have the holes, you have this little hut here that's kind of like a greenhouse on a sled. You push it over there, so it's kind of nice and warm. And then we have these antennas here, and we can lower them into this hole. Then we have a big box in the middle of nowhere where all these signals are recorded, solar panels for power. And this is currently something we're building. And it's going to be a couple of years till we have actually a chance to, till our detector is big enough and has run long enough that we actually have a chance to see these neutrinos. But can we go to even higher energies? And yes, you can. So if you want to see even more eyes, what you do is you take your antennas and you put them on a balloon. And there have been a bunch of, has been an experiment called ANITA. So there were 4 flights of this experiment. So there's ANITA 1, 2, 3, 4. That looks like this. So it's basically a balloon with a bunch of radio antennas on there. And right now I'm also working on the successor to this, which is called POEO, which is just basically a bunch, even more antennas on a balloon. And the idea is basically the same. You have a neutrino interact in the eyes, produce a radio signal, and then hopefully you can see this from the balloon. Having it on the balloon is good in the sense that you can see a lot of eyes from there. The problem is, of course, you're further away from the radio signal or from the shower. So this only really works at these very, very highest energies. And there's kind of a happy coincidence that allows us to do this because Antarctica just generally is a really good place to have high altitude balloons. Because in the summer, you have this kind of wind pattern that just, if you launch a balloon, it's just going to go in a circle for a really long time. So that's why a lot of ballooning for like weather observations, all that kind of stuff happens in Antarctica. And it just happens to have a lot of ice. And also, if your balloon crashes, like at the end of the time, usually either because the people running the station want to go home, or because it's kind of drifting off land, you can just cut it, and then it's gonna crash down, and you don't really have to worry too much of hitting anyone because there's no one there. So this is from one of the ANITA flights when it came down, and we just got lucky that this happens to be where a lot of ice is, and ANITA actually has seen something fairly weird. That's called the ANITA mystery events. So what ANITA can see is also these air showers from cosmic rays also produce radio signals. You can see them. And you can also see reflections from these cosmic ray radio signals bouncing off the ice. What that does is it will flip basically the polarity of the signal. So this is what you can see here. So these, hang on. This here is from a cosmic ray signal that bounced off the ice. This is from a cosmic ray that we see directly because it's kind of just skimming the Earth. But then there's also this signal, which is weird because it looks like a cosmic ray, but it's just coming from like down here. And we don't really know what it is. It's called, there's multiple of these, so it's not just one fluke. We don't really know what it is. It might just be that sometimes the ice does weird stuff to radio signals. It might be some weird interaction with cosmic rays. We really don't know. If you asked New York Post, it's a mirror universe where time runs backwards. So don't get your news science news from the New York Post. I mean, they're not by far not the only ones who run with this headline. So sometimes, this kind of news gets overstated. So this is what we're working on right now. POEO is hopefully going to clear this up. POEO is going to launch in the winter next year, hopefully, if everything goes to plan. And yeah, we can talk about what we do then. Just before I answer questions, let me just give a little outlook for next week, because unfortunately I couldn't find a good segue into this, but next week we're going to talk about gravitational waves, which is a fairly new development that we can just see space-time itself changing from certain sources in space. And to me, it's kind of weird that in like 10 years, it went from something really crazy to something that's now basically routine. So yeah, that's what we're going to talk about next week. Yeah?
Where does the research that's done at 3,000 meters in a gold mine in South Africa fit into the evidence for neutrinos?
You mean the Homestake Mine experiment?
No, I have a colleague that did research at 3,000 meters in a gold mine in South Africa on neutrinos. I wonder where this evidence fits into
I don't remember which particular experiment it is. So usually you build these neutrino detectors very deep underground just because that shields it from a bunch of stuff. So there have been other experiments that I didn't have time to get into for this solar neutrino problem. The most famous one is called SNO, Sudbury Neutrino Observatory in Canada. And you can build detectors that can distinguish that basically can have interactions that can be done by all three neutrino flavors, or ones that can only be done by electron neutrinos. And that was actually what finally nailed neutrino oscillations down and showed that this was where the solar neutrino problem came from. I think that South African one was something in that direction, but I would have to look it up. Yeah?
You mentioned that neutrinos travel about the speed of light. How is that determination made?
So the best determination comes from this 1987 supernova, because it's, if they, it's in another galaxy, so it's a really long distance away. So even if they only travel very, very slightly slower than light, you would expect to see them, years later, which we didn't. And from that, you can have constraints on how much slower than the speed of light they go. And from that, you can also constrain the mass. And for a really long time, this was actually the tightest constraint on the masses of neutrinos. Yeah?
I heard that there's a possible fourth type of neutrino, a sterile neutrino.
Yes.
Is that thing you look for in places like IceCube?
IceCube does that. Hang on. Okay, so basically the reason you want a sterile neutrino, or why a lot of people, including me, think sterile neutrinos are a really good idea, is that if you ask, why do they have masses and why are these masses so small, you could explain this by there being a fourth very heavy neutrino that then basically interacts with these other neutrinos. But it's so heavy that the charge particle that corresponds to it is so heavy that you basically cannot produce this particle because the neutrinos just don't have enough energy. So that's the idea behind it. And if this neutrino exists, then what should happen is that basically, in addition to these oscillations, there should be a fourth one where the neutrino, for example, your electron neutrino oscillates into this fourth state. And so what you would see then is that this dependency on the distance and the energy will change, and you basically see neutrinos disappearing without them appearing anywhere else. And IceCube does basically the same that Kamiokande did, where it looks for neutrinos in different directions. June, that's a building at Fermilab, that's one of its main goals is to check for this. But so far, there's been no evidence. But I think it's a really good theory.
Is it still considered a good candidate for dark matter?
Yes, I think mostly it is. There's different ways you can have this sterile neutrino can have different properties, and under certain circumstances, it could be a candidate for dark matter, yes. Yeah, back there?
The arrest mass for the neutrinos must be awfully small. I assume that the energies on your neutrino oscillations are the product of the high speed being close to the speed of light.
Yeah, the masses must be tiny. So we use this kind of weird unit in particle physics called electron volt, which is if you have a voltage of 1 volt and you run an electron through it, afterwards it's going to have this energy. And so, for example, protons and neutrons have roughly a mass of giga electron volt, so that's billion electron volts. Neutrinos have less than an electron volt. So those must be really, really tiny. And that's one of the reasons why everyone just assumed they didn't have mass, because it's so tiny. Why wouldn't it be zero?
Neutrinos have a spin.
Yep. Yes. Yeah.
I noticed there are quite a few detectors across the Earth. Would there be any advantage to having one on the moon?
Well, I mean, definitely none that would justify the incredible cost.
It's peanuts, believe me.
So tell that to the National Science Foundation. And so, I mean, what would be interesting about having a detector on the moon is that you don't have air showers, or you don't have them in the same way. You know, you don't have atmosphere, so you don't have cosmic rays interacting with the atmosphere. You would have them interact on the surface. So, and I mean, a big problem for IceCube and detectors like that is that a lot of the neutrinos they're seeing is actually from atmospheric backgrounds. So what it would allow you to do is basically see neutrinos at lower energies, because right now on Earth that all gets basically overwhelmed by atmospheric neutrinos. So that would be a use case. But yeah, it's going to be hard to convince anyone to give us the money to do that, unfortunately. Yeah?
If you were an alien and traveling very close to the speed of light, could you catch up to a neutrino so you would observe it at rest? And what experiments could you do if you had one or more neutrinos at rest?
So there is actually something kind of like that. Hang on, where are they? Here. So there are these guys here, the cosmological neutrinos. These are, I mean, they're still like basically speed of light because the masses are so tiny, but these are like very, very low energy neutrinos. And what they basically are, they are kind of the neutrino equivalent for the cosmic microwave background. Because, you know, the cosmic microwave background was basically you had a really hot, dense plasma, and then eventually that got transparent, and then that's how you get the cosmic microwave background. The interaction, like the probability for a neutrino to interact, actually depends on its energy. So the higher the energy is, the more it will interact. So in the extremely early universe, and this is like microseconds after the Big Bang or even earlier, like very, very early universe, because there was so much energy on such a small volume, everything basically was really high energy. And so at the time, neutrinos actually did interact quite a lot. So basically, matter was transparent for them. But then as it cooled down, they lost energy, and eventually they lost so much energy that everything was basically transparent again. And that's basically what happened to these. So this is kind of the, as I said, the cosmic microwave background equivalent for neutrinos.
The lower right part of the graph?
Yeah, the top left, the cosmological.
The top?
Yeah. So these are incredibly common, but the problem is because they're from this extremely early universe, they're also extremely redshifted. So they are very low energy, and unfortunately there's really no good way to detect them because they have so little energy. There is one experiment trying to do it right now. It's called Ptolemy. It's kind of controversial because most people don't think it's going to work. But yeah, it would be really cool if we could detect them, but there's no good way to do it, unfortunately. Yeah?
Summarize what you said to make sure I understood what you said. The Big Bang, the initial Big Bang explosion, it did produce neutrinos,
Yes.
but we can't measure them.
Yes.
They're too weak.
Well, because this happened so extremely early, there has been, like, these are, you know, the further back in time you go, the more redshifted everything gets. So they are so redshifted that they have so little energy that you basically can't really get them to interact with anything. Because, you know, for example, like the energy is less than the mass of an electron. So if they interact with anything, they're not going to produce an electron. And if they interact, you know, if they just have give some nucleus or something a little bump, that bump is going to be so tiny that how you're going to see it. So it would be cool if we could, but it's going to be hard. Okay, I don't see any more questions. Last chance. Okay, thanks.